Our special Lorenz transformation should be something we can write down as a 4x4 matrix, which will act on the 4 vector M0, 0, 0 and give us P0, P1, P2 and P3. Now, this actually tells us something about the Lorenz transformation, but frankly, it doesn't tell us much. And you don't expect this particular condition to tell you all about L anyway, simply because there should be infinitely many different Lorenz transformations which will actually give rise to the same result. After all, if you have found one Lorenz transformation which will work, then what you can always do is first carry out an arbitrary rotation, since that will not change M0, 0, 0 at all. Then carry out the Lorenz transformation that you have found out. And after you have done that, carry out any arbitrary rotation about an axis which points in the direction of the final momentum. That also will not change either P0 or the P vector path. So you see, there are infinitely many possible Lorenz transformations which will do our job. At this point, our job is to find out one specific Lorenz transformation which will do this. And we are going to use that as a standard Lorenz transformation. But before we go on to do that, let me point out about how much I can learn about this matrix L simply by looking at what it is supposed to do. And before I go there, let me just point out that P0 basically is M C gamma, but since C is 1, it is just M gamma for us. And P1, P2, P3 are just M times V1 gamma, M times V2 gamma, and M times V3 gamma. These are the three components of the spatial part of the momentum vector. And from that, you can immediately read off that P0, P1, P2, P3. If you want to get that from M0, 0, 0, this first column of L has to be gamma. Then you must have V1 gamma, V2 gamma, and V3 gamma. So the first column is known. Frankly, nothing else can be said about the other elements, other 12 elements of this 4x4 matrix, by looking at what this matrix does to M0, 0, 0. Of course, those elements cannot be completely arbitrary because we need this transformation to be a Lorenz transformation. So the basic property of a Lorenz transformation, L transpose eta lambda equals eta, has to be satisfied by this matrix. But apart from that, there are no restrictions. So as I have already said, there are infinitely many choices. So how do we go about choosing a special Lorenz transformation, which we are going to take as standard? Of course, the simplest Lorenz transformation or simplest Lorenz boost is one along a coordinate direction. We usually talk about transformations about the x-axis, but we can talk about any one of the axes. But what we will do now is just exploit that. In fact, we will start with a rotation which will change the final direction of our momentum, the desired direction, into one of the three axes. Weinberg chooses the z-axis or axis number 3. Then boost properly so that the particle now in this boosted frame has the correct magnitude for the momentum. And then we are going to carry out the rotation, the first rotation in reverse, so that the z-axis now goes and points towards the direction of your final momentum. And then you are done. You are ending up with getting the momentum correctly in the proper direction and the proper magnitude. Notice this is just a spatial momentum, but since P0 is square root of P vector square plus M square and M is fixed, getting the 3-vector part right is all you really need to do. The 0th component will take care of itself. So what we will do is start with a rotation r, which will have p hat, that is the unit vector in the direction of the spatial momentum, as an argument. What is the job of this r of p hat? It rotates the 3rd axis so that it lands up being in the correct direction of the momentum. Now this particular rotation can have a degree of arbitrariness into it. After all, we could just start with a rotation about the z-axis, any rotation whatsoever, then carry out whatever rotation you have found out, and then also carry out a final rotation about the new p hat axis. That also will carry the 3rd axis or the z-axis into the direction of p hat. Later on, we will have to deal with a standard version of rp hat when we talk about massless particles. But as we will soon see, the precise form of r of p hat doesn't matter as long as it does our job, as long as it carries the z-axis into the direction of p hat. So according to what we said a while ago, what we will do is first carry out the inverse of this r inverse p hat, because we want to take p hat into the z-axis, then carry out a boost which gives the momentum the correct magnitude. So this boost should depend on the magnitude of p. And finally, we will rotate back to the correct direction, or the z-axis goes back to the direction of p hat. And as a result, what happens at the end is our initial vector, which had 0 for spatial momentum, has been boosted properly to the right magnitude and has been carried into the right direction. So this is what we are going to take as our LP. Now for an explicit form for this. The explicit form for B of P hat is actually pretty straightforward. Everybody knows what that is. Okay, anybody who has studied basic special theory of relativity knows what this should be. Let me just remind you that in special theory of relativity, the Lorenz transformation that you study at the very beginning is a boost about the x-axis in the forward direction. So there the second observer is traveling along the positive x-axis with a speed v, or beta, because we are using c equal to 1, so beta, v by c is the same as v for us. And for that, the Lorenz transformation matrix is gamma minus gamma beta 0 0 minus gamma beta gamma 0 0 0 0 1 0 0 0 0 1. Note, however, that this is really not the boost we want. As the result of our boost, our particle should have a momentum. Our particle, which was at rest in the original frame, should have a momentum along the positive z-axis. But that is possible only if our second observer, the observer for whom this Lorentz boost is traveling to the left and not to the right, along the negative axis. So that's easily remedied. All you have to do is change the sign of beta. So the matrix would have been gamma, gamma, beta, gamma along the top corner and identity along the bottom corner if this had been a boost along the z-axis, along the x-axis. But what we need is a boost along the z-axis, and that can be easily obtained by just moving the rows and columns around in this matrix. Of course, not this matrix, but the matrix with the sign of beta changed. So the boost that you're looking at will really be this. These two rows simply say that the x and the y components will not change, and these tell us that the temporal and the spatial components will mix. One word of warning: if you were to look up Weinberg to match these formally, you will find that the results in Weinberg's book does not look exactly like these. And the reason for that is Weinberg lists his rows as 1, 2, 3, 0. So in fact, what we have been calling M000, Weinberg calls 000M. And similarly, Weinberg would have a much neater looking form for his B of P. If he had written that down, I think he has. And in his B of P, you would have had the identity matrix at the top left corner, because X and Y axis would come first, then would come Z, and then would come T. So you will have gamma, gamma, beta, gamma, beta, gamma at the bottom right corner. Looks neater, but essentially the same thing. And Weinberg also does not use gamma beta, he uses root over gamma square minus 1. But you should be able to convince yourselves that these two things are exactly the same. Let us now work out an explicit form for L of P. We need to first put in a rotation R of P, P hat. Now in the 4x4 matrix form, it's going to be simply 1, 0, 0, 0 and zeros down the column here as well, simply because the time does not get involved in rotation at all. And this 3x3 piece here is actually the three-dimensional rotation matrix, which we are just going to call R for the time being. Remember, as of now, this R could be any rotation which carries the third axis into our final direction for P hat. So there is a bit of ambiguity about which R we are going to write down here. But as we will soon see, that will not affect your final result. Then of course comes a boost, gamma 0, 0, gamma beta, 0, 0, gamma beta, 1, 0, 0, 0, 1, 0, 0, 0, gamma. And finally, you have the inverse of this matrix, or basically this block version with an R inverse sitting here, but in the three-dimensional world, R inverse is the same as R transpose. You can just as well write R transpose. Now, multiplying 3 4x4 matrices may look like a tall order, but it's really rather simple here because of the nice block structure which two of these matrices have. And you can make life simpler for yourselves just by thinking of this 4x4 matrix, the boost, as also one which has the same block structure. So here you have blocks which are 1 by 1, then you have a 1 by 3 row vector, then you have a 3 by 1 column vector here, and then a 3 by 3 matrix. Now multiplying blocked matrices can be done exactly the same way as multiplying ordinary matrices, as long as the blocking is consistently done. So, for example, to get the 1, 1 element of the product of these two matrices, you will take the first row here, as always, and the first column here, but you will essentially take this element, multiply with this element, you will get 1 times gamma, which is a number or a 1 by 1 matrix, whichever way you look at it. Then you will have this row vector 0, 0, 0, the 1 by 3 row vector, multiplying the 3 by 1 column vector 0, 0, gamma beta, and that will give you a 1 by 1 matrix. Of course, in this case, it just gives me 0. So I can easily add that to the gamma that I already have to simply get a gamma in this part. Now, of course, I still will have this block structure here. For the 1, 2 element, that is this element, we need to take this row and this column. 1 multiplies the row vector 0, 0, gamma beta to give you a 1 by 3 row vector. The 0, 0, 0, which is 1 by 3, multiplies 3 by 3 matrix R to again give you a 1 by 3 row vector. But in this case, the row vector is trivially all zeros. But in any case, you are supposed to add these two row vectors together, and what you are going to get here is simply 0, 0, gamma beta again. That's simply 1 times this row vector. Well, the 2, 1 element, this row times this column, 3 by 1 multiplied by a number gives you a 3 by 1 column vector. And then this R multiplying this column vector also again gives you another column vector. And these two have to be added together. Of course, the first 3 by 1 column vector times gamma gives me nothing. So all you have is R acting on 0, 0, gamma beta. Well, what about 2, 2? Again, that's pretty straightforward. You take this row, this column, and it's easy to see. What you're going to get is R times 1, 0, 0, 0, 1, 0, 0, 0, gamma. Once again, using blocked matrix multiplication rules, we can easily carry out this multiplication, and the result is simply the following. Get gamma on the right hand corner, then you have R0, 0, gamma beta down here, that doesn't change. What you have on the top right corner, that is this piece here, is just 0, 0, gamma beta acted upon by the transpose matrix RT. And finally, the 3 by 3 block that is sitting here turns out to be R 1, 0, 0, 0, 1, 0, 0, 0, gamma acted upon on the right by R transpose. So this is our final product matrix L of P. Let us now examine this matrix in somewhat more detail. The top corner, of course, there's not much to say about it. This is the gamma factor corresponding to the momentum. Now, what about this thing? Note that R0, 0, gamma beta is the result of the rotation matrix R acting on a column vector which is initially in the z direction and has magnitude gamma beta, which is essentially the magnitude of the momentum divided by the mass. Of course, we are using C equal to 1 here. Now, what does R do? It changes the z direction into the direction of the final momentum. So, 0, 0, 1 under the action of R would essentially become the unit vector in the direction of the momentum that we want. So, basically, the resulting thing here essentially is the unit vector in the direction of the momentum, P hat, times the magnitude, which is, of course, gamma beta. You can, of course, also write this, since gamma beta is actually the magnitude of the momentum, spatial momentum, up to the mass factor. You can actually write this as P vector divided by M. So the 0, 1, 0, 2. So the 1, 0, 2, 0 and 3, 0 components of this 4 by 4 matrix are simply nothing but P1 by M, P2 by M, P3 by M, or you could write them as gamma beta times P hat 1, P hat 2, P hat 3. To be more precise, the 3 components of the unit vector in the direction of the momentum. And let me remind you once again, gamma beta is the same as square root of gamma square minus 1, which is what Weinberg uses in his book. Now the rest of the top row is filled up by a row vector, a 3-element row vector, 1 by 3 vector, which is essentially the transpose of this vector. So it has the same components. So we can immediately write down the following components for this L of P. L P's 0, 0 component, we have already seen that, that's simply gamma. L of P's I0 component, which is what we have seen right now, where I runs over 1, 2 and 3, are exactly the same as L of P's 0 ith component is given by P hat I root over gamma square minus 1. I am writing this here simply because that will make the connection with Weinberg's results direct. Although I could write gamma square instead of gamma square minus 1, I would have personally preferred to write gamma beta. Or just use the fact that these are really the momentum's ith component by the mass. So what is left are finding out the purely spatial components LPIJ. And that looks like a bit more work. After all, this is a 3x3 matrix acted upon on the left by R, on the right by R transpose. So basically you are carrying out a similarity transformation using R and R transpose. Let me point out, at least up to this point, we have been able to write down the components of L of P, the ones we have been able to find out, using just numbers which we can get from the final momentum. This can be a bit of a surprise because R, after all, is somewhat arbitrary. You do have infinitely many choices of a rotation which will carry the Z direction into the final momentum's direction. Despite that, these numbers are uniquely determined by the momentum components, the final 4 momentum that we want. What about the spatial part of this matrix, LPIJ components? Will this result hold for that as well? So to check that, let us write this matrix 1 0 0 0 1 0 0 0 gamma slightly differently. I'm going to write that as identity plus 0 0 0 0 0 0, because identity takes away the ones here, and 0 0 gamma minus 1, and apply R and R transpose on that. Now, of course, R transpose, the first term is simply identity. R transpose, remember, is R inverse. The second term is simply gamma minus 1 multiplied by R 0 0 0 0 0 0 0 0 1 R transpose. Now, a trick will actually make it easier to see exactly what this term is going to be. So let me just write this down. 1 identity plus gamma minus 1 times R transpose. But the matrix here, the 3x3 matrix, can actually be written down as 0 0 1 multiplied by the row vector 0 0 1. Can immediately check that this product is nothing but this particular matrix. In more formal language, you would say that this essentially is a projection matrix to the third direction. And that's why you take the third direction's vector and its corresponding transpose, and you multiply them together to get the corresponding projection operator. If you have not handled projection operators before, don't worry too much about this particular thing that I said. You can, of course, directly multiply out the column vector by the row vector and verify that this is really the same. But now comes the point. R acting on 0 0 1. What is that? That's nothing but a vector which is in the direction of the final momentum. Remember, we have started with the z-axis here, 0 0 1. Applied R on it. So you should get a vector in the direction of the final momentum, but which has magnitude 1. Rotation, of course, doesn't change the magnitude. So this is nothing but a unit vector in the direction of the momentum. That is our p hat. So basically, R001 will give me a vector with 3 components, p hat 1, p hat 2, p hat 3. And this is nothing but its transpose, so this will give you p hat 1, p hat 2, p hat 3 again. And so, the ijth component of this object can be written down rather easily. It's going to be ijth component of this whole thing, which is delta ij coming from here, plus gamma minus 1 times the ijth component of the product of this column vector with elements P1, P2, P3, P hat 1, P hat 2, P hat 3, and this row vector with elements P hat 1, P hat 2, P hat 3, and a moment's thought would convince you that this product is nothing but this. So that gives us the final part of the matrix. LP hat ij is actually delta ij plus gamma minus 1 P hat I, P hat j. So once you know the final 4 momentum that you're aiming at, you can find the standard Lorentz matrix which acts on M000 and gives this momentum P as a result. And the components of this matrix can be written down entirely in terms of the 4 momentum itself. Note that once again the infinite degeneracy in R and R transpose does not really show up, not even in the spatial part. So you can uniquely find out the answer for L of P just from the description that we have given of it. That is, first apply R inverse P hat to carry the direction of the momentum to the z-axis, then boost along the z-axis to get the appropriate magnitude for the momentum, and then finally rotate back to get the z-axis back in the direction of the final momentum. This gives us a unique L of P, which we can use then to figure out the way in which we would define psi p sigma, starting from psi k sigma. Also, you could use this to figure out the W lambda p's and hence figure out the way in which these wave functions transform. At this stage, you may be wondering why we needed the R inverse P hat to begin with. After all, the vector it's going to act upon is the 4 vector M000, and the initial rotation, the first one, that is R inverse P hat, does nothing to this vector. So could we have just dropped this and found out another version of L of P? Of course we could have. We could have used that L of P, and I will let you figure out why at the end of the day using such a different L of P does not really change our conclusion about what Lorenz transformations do to states. However, let me point out why exactly this particular form R of P hat B mod P R inverse P hat is very, very useful. In fact, you may have already realized that. If we are stopped short of using this one, that is, we are just stuck to the first 2 operators R of P hat, B of mod P here, then finally after you do the multiplication, you would end up with just this matrix. Now why is this not such a great thing? Because this particular quantity R acting on 10001000 gamma will depend specifically on the rotation that you are carrying out, the standard rotation, which you have decided will take your z-axis to the p hat axis. And the ambiguity there will stay in the L of P. The form that we have taken is unambiguous in the sense that at the end we can write down everything in terms of just the 4 momentums components. That is the target 4 momentum that you want. You're just using the components of that. And that's all L of P really depends upon. So that kind of independence from this arbitrariness of the choice of R is one very good reason why we should take this particular form. There is another very important reason why we like this particular form, and I'm going to come to that in a little while. Let us now take a look at a few examples to try to understand what these actually mean in action. The first example we will consider is actually a very, very simple example. Consider a particle moving with some velocity or with some speed v along the z-axis. Of course, whenever you make such a statement, it's always with respect to some observer. So this is with respect to an observer O. And let's say the state of this particle is defined by this psi p sigma, where p, of course, is a form momentum. M gamma 0, 0, mv gamma. Now, the question is, if we observe this same particle from another observer, say O prime, what state will O prime see? And this O prime is an observer moving with speed, let's say u, along the z-axis with respect to O. So here we are talking about an observer who is moving with respect to O in the same direction as our particle that is being observed. So what do you expect the observer O prime to see the state of this particle to be? That is, for this particular Lorenz transformation which carries O to O prime, what will u lambda acting on psi p sigma be? Now, we don't really need to carry out a detailed calculation to check what this is going to be. A simple argument would work. But first, let me point out that for an observer who is just moving along the z-axis, L of p is rather simple, because you don't really need to rotate the direction of the momentum back to the z-axis. You don't really need R of p hat at all, or you could just choose R of p hat to be identity, which means that the simple form for L of p will be B mod p. So it will just be a boost. Lambda p, the form momentum that observer O prime sees, is a different form momentum, but it's again along the z-axis for this observer. So L lambda p will also again be just a boost. Now, what simplifies the discussion a lot after this is the little group element that we are looking at for this particular situation, W lambda comma p. L inverse lambda p, lambda L of p, is composed here of three distinct boosts. L of p is a boost along the z-axis. Lambda, the boost which carries O to O prime, is also a boost along the z-axis. And L inverse lambda p is also a boost along the z-axis. Now, if you have boosts in the same direction, they combine to give you boost in that direction. As a result, W lambda comma p, it has to be a boost along the z-axis. On the other hand, we already know from basic theory that W lambda p is an element of the little group for our standard 4-vector M000, which means it has to be an element of SO3, or put in more simpler words, it has to be a rotation. So now we see that our W lambda p in this particular example has to be both a boost along the z-axis and a rotation, and that has only one possibility. There's only one boost along the z-axis which is also a rotation, which is a boost through no velocity at all and a rotation through no angle at all. So has to be the identity. This is the only boost which is also a rotation. So in this particular example, W lambda p is the identity, hence d sigma prime sigma the components of the matrix which represents the identity are nothing but delta sigma prime sigma. And so your final result here will be simply this. U lambda acting on psi p sigma for our particular example will simply pick up a normalization factor. This is because of the kind of normalization we have chosen for these wave functions. But other than that, the only effect which this Lorenz transformation will have will simply be to change the momentum. The sigma indices will not be affected. Remember, d sigma prime sigma is really delta sigma prime sigma, so the sum over sigma prime becomes absolutely trivial. So this is one case where the situation is really very, very simple. All that happens is that the momentum of the corresponding state changes and the normalization factor changes, but that's rather trivial. Nothing else actually changes here. Okay, let me stress that is because we chose a very, very simple scenario. Particle was moving in a particular direction with respect to O, and the new observer, O prime, is also moving in the same direction as the particle was. If the observer were to be boosted, no rotations, nothing very complicated, just a boost, but in a different direction, then things will get much more complicated, also much more interesting. However, the algebra here is rather messy, so I don't really prefer doing it here on screen. Seeing a lot of nasty algebra worked out on the screen doesn't really add to understanding. So I would urge you to actually try doing this yourself. You can just take a simpler case, say particle moving with speed v along the z-axis as in this example. But let's say O prime is an observer moving with speed u along the x-axis. And try to figure out what w lambda p will be for this particular case. And then try to find out what the resulting state will be. Of course, the resulting state will now depend on exactly what the matrix D is. In our previous example, W was just the identity, so D had to be the identity no matter what particular kind of particle you were talking about. But if you're talking of a spin J particle, then you would need to use a specific representation matrix for the spin J. Well, at least spin half should be familiar from elementary quantum mechanics, maybe spin 1 as well. Try to see whether you can get the thing done right. Let me stress at this stage that this is going to be rather lengthy and laborious, not very difficult, but lengthy none the same. As you will see, our next example has rather important physical consequence. This is simply a particle moving with 4 momentum p with respect to some observer O. I am putting no restrictions whatsoever on this 4 momentum, it could be anything. But the restriction that I have put is on lambda, the Lorenz transformation that takes you to the observer O prime from O. We are considering a situation where lambda is just a rotation. So physically we are asking for what happens to the vectors which describe our state when you rotate your coordinates. We already know an answer to this from non-relativistic quantum mechanics, and the theory of rotations in quantum mechanics is actually quite extensive, and it has given us effectively the theory of angular momentum and all this stuff about Clebsch-Gordon coefficients and all this other machinery. Now, let's take a look at what a rotation of coordinates would do in relativistic quantum mechanics. Now, for this, what we need to do is, of course, figure out what this little group element W is. So, we want to look at W, lambda p, but lambda is this curly r, a rotation. Of course, this is L inverse, this rotation acting on P, then this rotation, and then LP. Now, let us use our specific form for LP that we know. So, this LP is going to be BR P hat, B magnitude of P, R inverse P hat. Of course, this curly R will be sitting here. Then you have to put in front of all this the inverse of L of Rp. So that of course is R corresponding to curly R acting on the P hat. Remember, P hat is a unit vector in the direction of the spatial 3-vector momentum, and the curly R actually rotates that, does nothing to the 0 component. Then you have B of magnitude of curly R acting on the 3-vector P, and then you have R inverse of curly RP. Let us now open out this inverse of the product of matrices using the standard rule for matrix inversion. That is, AB whole inverse is B inverse A inverse. So this comes to the front, becomes inverted. So this is R curly RP hat. Now you have B inverse for this boost. But notice that the argument here is a magnitude of curly R acting on P vector. But since rotations don't change magnitudes, the argument is the same as magnitude of the original P vector. And finally, you have R inverse curly R P hat. That is of course followed by what you already had, that's curly R, then you have RP hat, then boost corresponding to the magnitude of P, then R inverse P hat. Now let us focus on these 3 rotations in the middle. Let me just change their color so that they stand out a bit. We are looking at this product of 3 rotations, which means you are going to apply RP hat first, then curly R, then R inverse RP hat. And let us focus on what this product of 3 rotations does to a vector along the z-axis. Now RP hat, by definition, will carry the vector along the z-axis to the direction of the momentum. Curly R will change that to the direction of curly R acting on the momentum. But R inverse curly RP hat will just undo that and bring the vector back to the z-axis. So the product of these 3 rotations together has to be a rotation, but it is a rotation which carries a vector along the z-axis back to the z-axis, which means it has to be a rotation about the z-axis. If you want to write down its matrix, the matrix version has to be of the following form. The time is not affected, so you have 1, 0, 0, 0 here, also zeros here. In fact, the z component is also not affected. So you have this, and the only components which are affected are the x and the y, or the 1 and the 2 components. And for some precise angle theta, the matrix must take this form. This is the final form which the matrix here must take. The important thing is, this rotation has to affect only the 1 and the 2 components of a 4 vector, not the 0 and the 3 component. On the other hand, the boost that we have here, that acts only on the 0 and the 3 component. Remember, that was the form gamma 0 0 gamma beta, 0 1 0 0 0 0 1 0, gamma beta 0 0 gamma. The precise form is less important than the fact that this boost acts only on the 0th component and the 3rd component of a 4 vector. It does not affect the 1st and the 2nd components at all. What that means, of course, is whether we apply this boost first on a 4 vector and then apply this rotation, or whether we do it in a different order, does not matter. You will always get the same result. The boost will independently change the 0th and the 3rd component, and the rotation, that is this product rotation, will independently change the 2nd and the 1st component. So, as a result, these 2 things commute. Of course, the great advantage of that is because they commute, I can move this boost right across this product of rotations to sit right next to B inverse mod P, and then they will just cancel each other out. But now notice that once the boosts have cancelled, things simplify considerably, because now R RP hat can cancel with R inverse RP hat, the RP cancels with R inverse P, and you are left simply with this very important result, that the W corresponding to a rotation is nothing but the same rotation. So remember, given a Lorenz transformation, you first find out the corresponding little group element, which is a rotation, and then look at the representation matrix for that particular rotation. If your Lorenz transformation happens to be a rotation, as in this example, the little group element that you use to figure out how the states are going to transform is nothing but the rotation itself. Same rotation. As a result, the theory of how these vectors transform under rotation of coordinates is exactly the same as a theory you had from non-relativistic quantum mechanics. So all the machinery we had learned earlier carries over intact here. Note that this is the reason why we had chosen L of P to have the particular form that we did, and we included the R inverse P hat at the back. This is the other reason for that, which we had mentioned a while ago. It makes the proof that the little group element for a rotation is the same rotation much easier to carry out. But this also justifies something we had already said in a previous lecture. We have been calling particles which are described as states indexed by this index J, particles which are spin J. We did that without much justification at that point. It was just a word for us at that stage. But now we notice that under a rotation of coordinates, these relativistic particles transform exactly the same way a spin J particle would, and hence the name spin J for this is perfectly justified. So to summarize, for a massive particle of mass m, you will have an index J which describes its properties under rotations. But not only that, this index J will also tell you how the states describing this particle will transform under any Lorentz transformation, and hence under any Poisson transformation. And the important physical result is this: a spin J particle will be described by exactly 2J plus 1 wave functions. It has 2J plus 1 independent states. So a spin half particle has 2 independent states, a spin 1 particle has 3 independent states, a spin 0 particle has only 1 independent state. Now I just mentioned that a spin 1 particle would have 3 independent states. However, the most familiar spin 1 particle that we have, the photon, actually does not have 3 independent states. We know that it has only 2. And the reason for that, of course, is the photon is not a massive particle, the kind that we have been describing here. It is massless. And for massless particles, the little group actually is different, the behavior is different, and that is what we are going to describe in the next section.